All right, so one of the very first tasks within our supervised learning modeling process is splitting our data. And we can see that if we look back at our image that kind of illustrates this process that we're going to go through. We have all our data here on the left. And the first objective, we want to split this into what we call our training data and then our test data. And most of the process of building, training, and evaluating a supervised learning model is all going to be done on this training data. We're going to set this test data to the side. So let's talk about what is the purpose of this data splitting procedure. And it really comes down to the idea of what we call generalizability. So when we are training a model, the objective is to use historical data or past data in order to predict some future outcome. And we want to predict that future outcome as accurately as possible. And so what we're actually going to do is build a model on a subset of our data. And we want to see how well will this model do on data that it has not seen before. So that's really one of the big reasons why we want to go ahead and split our data. All right, so what we do is initially we typically split our data into a training set and a test set. Now the training set, like I said before, is pretty much the data that we're going to use for developing any new features that we want in our data, for training any of the machine learning algorithms, for tuning hyperparameters, and then comparing across many different models. So we typically train many different models to try to find the one that does best. And so we need to compare how these models perform. And we're doing this whole process on our training data. Now, once we have determined that some final model is the optimal model or the best model that we could actually find, what we're going to do is now take that model and we're going to apply it to the test data. And that is going to give us the estimate of our what we call the unbiased assessment of the model's performance, or the generalization error. So the test data is what provides us a good idea of what we can expect our model to do on new, like future unseen data. All right, so the important thing here is we develop we extract our training set and our test set, and we set the test data to the side. We are not going to use that at all during the entire model building process. We're going to use it at the very end to see how well the model that we have selected will perform to unseen data. So don't touch it, put it in a vault, leave it to the side, and we're going to do everything on the training set. All right, so what's the right size of our split? Well, typically what you'll hear is you'll see roughly in the range of 60 to 40%, meaning 60% of our observations go into our training data, 40% go into our test. We also see splits of 70 and 30, so 70% in our training, 30% in our test. Or we'll see 80-20, 80% in our training, 20% in test. And basically any of these ranges is roughly good. On what I would consider just an average type of a data set, I most commonly use a 70-30 split. But typically if you're doing this 60 to 40 all the way up to 80-20, you should be just fine. Now, we may want to deviate or think more seriously about what the right split size is. As the size of our data sets that we're using either changes to be very small data sets or very large, right? So as an example, if we have a data set where there are less than 500 observations, well, what can happen now if we spend too much of our data on the training, if we put too much of our data into the training, meaning we put up to 80% or even more than 80%, this may not allow us to get a good assessment of the predictive performance, okay? And we may find a model that fits the training data very well, but it doesn't generalize well. But now if we don't have enough data in our test set, then we actually don't get a good assessment of the model parameters. If we change or tweak the model parameters in our algorithm, how does that perform, right? Or if we have a data set where we have a lot of observations, basically as our observations are over 100,000, well, now we can actually get away with having a smaller less amount in our training. So we could actually have less than 60% in our training data. And that's typically because we have such a large data set, it's easy to get a good representative sample with less than 60%. Right? And then also we need to understand how many columns do we have? How many predictor variables do we have within our data? Right? As our predictor variables actually approach or become greater than the number of observations, then we often need larger sample size in order to identify relationships or signals within our data. But for the most part, for the typical average data set, especially for the data sets we'll see in this class, in this course, most of the time, this 70 to 30% is roughly sufficient for our needs. All right, so there's two very common ways of splitting our data. I mean, there's actually many different ways of splitting our data, but the two most common ones that you will see are simple random sampling and stratified sampling. So simple random sampling is literally just randomly selecting, let's say, 70% of our observations from our data set to be in our training, and then we use the other 30% in our test set. Now, if we do what's called stratified sampling is designed to preserve the distributions within our data. And most often what we do is we will stratify our sampling based off of the target variable. And the objective here is that we want to preserve the distribution of that target variable, whether that's in a regression model or a classification. We want the training and the test sets to both have as close to similar distributions of the target variable or the outcome variable as possible. All right, so how do we implement this? So if you want to do sampling, we will use the initial split function within R. And this is provided by Tidy Models. And all we do is we pass it our original data set. We tell it the proportion, right, or the split that we want to. So in this case, we're saying we want 70% of our data to be in the training set and 30% be in the test. If we wanted to have 80% in our training, we just change this to 0.8. And then here's an optional input that we can supply. And this means we want to stratify, right? So this gets to, we want to use this stratified sampling where our training and our test sets will have similar distributions of the sale price, which, if you recall, is our target variable. Now, if we do this on the classification data set that we have, which is called attrition, right? We have the same process. We're going to do an initial split. We're going to use a 70% split for our training set, 30% in our test set. And then we want to stratify on the attrition variable. Right, so we want to make sure that the train and test set both have the same proportion of this variable in it. Okay. All right. So how does that look? Well, we talk about we want to make stratifying basically is trying to make sure that the distribution of our target variables are similar in both data sets. Well, we typically want to validate that this is actually happening, and you want to do this validation whether or not you use stratified sampling. So if you use simple random sampling, you also want to make sure that the distributions are relatively similar. Right? So how does this look? Well, if we look at the Ames data, right, we could look at the distribution of our sale price variable. Recall, this is the target variable that we want to predict. And so we can see here the black line is the distribution of the sale price in our training data, and the red line is the distribution of sale price in our test data. And you can see that, in fact, their distributions are very similar. So we should be good to go there. Now, in a classification model, right, what we care about is that the ratio or the proportion of the responses, basically attrition is binary, where it's either yes or no. Those are the two options for the response variable. We want to make sure that the proportion of yeses and nos are similar in both the training data and also the test data. So we see here that in our training data, we have just under 84% no's and we have 16% yeses. And if we look at our test set, we have almost the exact same ratio. So we are good there, both the training and the test set for both of these data sets have very similar distributions for the response variable.